So now we're going to dive into our second multiplication operation. So what we're going to do is we're actually going to build what this cross product is, because it's going to be a super important vector for us. So one thing that's going to be essential is we're going to need to find, if I have two vectors, a third one that's going to be orthogonal to both of them. And so this is where we're going to build this idea of a cross product. So if we have two non-zero vectors, let's say A, which has components A1, A2, A3, and then we have vector B, which has components B1, B2, B3. So if we have these two vectors, it's going to be very useful to find a vector C that's orthogonal to both A and B. I have zero idea what the relationship between A and B are. They could be orthogonal themselves. They could be parallel. They could also just have a random angle between them. So to give you a visual, essentially, if I have this vector here, A, and then I have another vector, let's say it points forward like this, B. What I want to do is I want to find a third vector that's going to come out, and this will be my vector C, so that it forms a right angle with A, and it also forms a right angle with B. So this is our goal. Can we figure out how to do that? So what we want is we want to find C, which I have no idea what the components will be, so I'm just going to call them C1, C2, and C3. So it's orthogonal, meaning if I take A and dot product it with C, I'm going to get 0. And if I take B and dot product it with C, that will also equal 0. Okay, so I want a vector that has components so that when I take these two dot products, I get this result. So that's my whole goal. Can I figure out what these components have to be to make that happen? And likely it's going to be in terms of the two vectors A and B that are given to us. Okay, so what we want is really the following. If I do A dot C, that's A1, C1, plus A2, C2, plus A3, C3 has to equal 0. And then also if I do B1, C1, plus B2, C2, plus B3, C3, this also needs to equal 0. So I'm going to call this first one equation 1 and the second one equation 2 because I'm going to refer back to them a little bit. So this is a system of equations. You can see it's technically two equations with three unknowns. A's and B's are all given, but C1, C2, C3 is unknown. So technically you do have a ton of solutions that are here. So what I'm going to do instead is I'm going to try to reduce this to a simpler system. So I'm going to go ahead and I'm going to eliminate the C3 component. So to eliminate C3, which is unknown, we need to have the same term in front of each of these, but opposite signs. So we're going to multiply equation 1 by B3, and then we're going to multiply equation 2 by negative A3. Because that will give me B3 here, that will give me A3 out front, but a minus sign, so they will be exactly the same coefficient, but opposite signs. So let's actually do that. I have to take this entire equation and multiply it by B3. And what that's going to give me is I'm going to have A1, B3 out front of C1. And then I'm going to also have A2, B3 out front of C2. And then I'm going to have A3, B3 out front of C3. And on the right-hand side, I still have 0. Now, when I take this equation, I'm going to multiply through by negative A3. That's going to give me minus A3, B1 attached to the C2. I'll go ahead and put parentheses here like this. Then I'm going to have a minus as well, and then B2, A3. So we'll put the A's first. And then that's attached to C2. And then the last one is also going to be negative, and it's going to be A3, B3 attached to C3, and still equaling 0 here. Okay. So if I go ahead and add these two equations together, it's going to eliminate my C3 terms, which is nice. So these are going to be gone. And then here, oh, I made a mistake here. This should be C1, because this should be the matching coefficient there. Both of these have exactly the same coefficient in front. And then likewise right here, these both have C2 attached to it. So I'm going to go ahead and factor things to make it a little bit easier. This is going to be A1, B3 minus A3, B1 attached to C1. And then for the second one, this is going to be A2, B3 minus A3, B2 attached to C2. And that's equal to 0. Okay. So I'm going to break this down because otherwise this is a lot of subscripts going on. This out front right here is just some number. And so is this. It is some number. These, however, are the things that I'm searching for. They are the unknowns. So if I have the equation, a solution to the equation P times C1 plus Q times C2 equaling 0 is the following. Okay? If I make this term Q, then I'm going to have to make this one, I want it to match, so it's going to be the opposite sign. So C2 will be negative whatever coefficient was out front here. Okay? To show you why that's the case, this would be P times whatever this coefficient is plus Q times the opposite of whatever was in front of C1. Those two cancel each other out here. So we're going to call this equation 3, basically meaning we're going to make this equal to C2, but opposite signs. And this is exactly going to be C1. So kind of matching it up here, we're setting C1 to be exactly this coefficient, and we're setting C2 to be the opposite of the coefficient in front of it. So what this means is a solution to equation 3 is we set C1 to be the exact same thing here. So it is A2, B3 minus A3, B2. And we set C2 to be the opposite of what's in front of C1. Okay. And these, I know what these numbers are because they're just the components of the vectors A and B. So that is a solution to this equation. Then I would still need what C3 is equal to. So if you remember going back through substitutions, we have C2, we have C1. I could then plug those things in and I can solve for C3. And I could sit here and do this, but I think at this point you're probably still like, what the heck is this girl doing right now? That's totally okay. We're going to go through this in a different way. So I'm going to skip that algebra, plugging those back in. If we substitute these back into 1 or 2, we can find that C3 is going to be A1, B2 minus A2, B1. So these are what the components are going to have to be to give us that orthogonal vector. We're going to define this to be the cross product. There is a little bit of patterns. You can see C1 deals nothing with A1 or B1. It deals with the other two. C2 deals with nothing A2, B2. And C3 deals with the other two components. So there is a nice pattern, and we're going to define this in terms of something else instead. But this formula is where our cross product comes from. So as a formal definition, if A has the components A1, A2, A3, and B has the components B1, B2, B3, then the cross product of A and B is the vector C, which we're going to denote by A cross B, hence we use the cross like the multiplication, which has exactly these components. So the first component is A2, B3 minus A3, B2. The second component is negative A1, B3 minus A3, B1. And the third component is A1, B2 minus A2, B1. Okay. So the key here that you have to recognize, the dot product results in a number or a scalar. This cross product is going to result in a vector, okay? So you have to make sure you understand that fundamental concept. You don't want to be taking a cross product and result in a number, or vice versa. So notice the cross product results in a vector. While the dot product results in a scalar. Okay. But like I said, you're not going to want to memorize this formula. That is a lot going on. So instead, we're going to talk about this using determinants. So if you saw in pre-calc when you went through matrices, you went through the process of calculating a determinant of a 2x2 matrix or 3x3. If you didn't or don't remember it, totally okay. We're going to refresh on that now. So here we can develop an easier way to find cross products by using determinants. So we're going to start with what is a determinant of a 2 by 2 matrix, and we say that is a determinant of order 2. So a determinant of order 2 is defined as the following. We use basically like absolute values around our matrix. Order 2 means it's a 2 by 2 matrix. Let's say it has the entries A, B, C, D. The way we find this determinant is we go ahead and multiply this main diagonal, and then we're going to subtract the off diagonal. So the result of this is a number. We get A times D, and then we subtract the off diagonal B times C. Okay. So let's do that with just a quick example. If I have the determinant of the matrix -1, 2, 3, -4. We're going to go ahead and multiply the main diagonal. So that will give us -1 times -4. And then we're going to subtract the product of the off diagonal. So that will be 3 times 2. -4 times -1 is +4, and then that becomes -6. So this determinant is -2. Be very, very careful when you do this. Super easy to make a tiny algebra mistake. And unfortunately, later on, that is going to make a big impact for us. Now, what we're working with, because we're dealing with vectors of 3 dimension, is we're going to need it to take a determinant of a 3 by 3 matrix. So we say a determinant of order 3 is defined in determinants of order 2. So this one's a little harder to write everything out because I can't use A through whatever. It's a lot of entries. So I'm going to say the first row has the elements A1, A2, A3. The second is B1, B2, B3, and then C1, C2, C3. So we're doing a process that's called expanding along the first row. So what we're going to do is we're going to take this first element, and that's going to get popped out. And it's going to leave me with finding the determinant of a 2 by 2 matrix. We'll talk about that in a second. Now it's going to alternate signs. So the first one is positive. The next one is going to be negative. And I'm expanding along the first row. So we're going to pop out this element, which is A2. And then we're going to need a 2 by 2 matrix after it. I always like to set it up doing this way just so I remember all of the signs. And then the third one, it goes positive, negative. So this one will be positive. And we take that last element, which is A3, and then we're going to be left with a 2 by 2 matrix. The way we figure out what goes in that matrix is we're going to strike out everything in that same row and column. So for A1, when I do that first thing, I'm going to ignore everything in the first row and column, and I'm going to write the resulting 4 elements that are left. So this will be B2, B3, C2, C3. Works really nicely on the iPad, a lot harder to do on a piece of paper. Now for the second one, we do the same thing. We strike out everything in the same row and the same column. And so what's left over are the elements B2, B3, C1, C3. And hopefully you can kind of see that pattern that's popping up. The first element has nothing to do with A1 or B1 or C1. Same thing here. The second has nothing to do with A2, B2, or C2. And then our last one, as you can guess, we're going to go ahead and strike everything in the same row and column here. And the four things that are left over are B1, B2, C1, C2. So nothing to do with B3 or C3 here. So what we're going to end up doing, these are going to be these resulting numbers that we had in these pieces, because you can see it's one thing minus another. We have this negative sign in the second component, which is exactly from here. And then the other thing that's going to happen is we want a vector. So these are going to be replaced by I, J, and K. So what we're going to do is rewrite our cross product now. So we can rewrite our cross product of A, which we're getting is that vector A1, A2, A3. I'm going to write this out as I, J, K. And the vector B, which is B1, B2, B3, we're going to write that in terms of I, J, and K. One thing you're also going to see real soon is I'm going to end up just not writing the little dots above I and J because it gets real annoying, or I just forget to. So if you see that happen, sorry, but that's what I mean. But we're going to rewrite the cross product of these two vectors as the following. So we know A cross B, based on our calculations, the first component has to be A2, B3 minus A3, B2. And that's the vector I attached to it because it's the first component. The second one is negative, and the coefficient out front was A1, B3 minus A3, B1. And this was J. And then finally, the last component is A1, B2 minus A2, B1. And that's our component K. So if you look at each of these, it's the product of something minus the product of the other. That tells us these are going to go on that main diagonal. And then the second one is going on the off diagonal. So we can rewrite each of these in terms of a determinant. So the determinant that results here is going to be A2, B3. And then the off diagonal is A3, B2. And that's times I. Then we have the minus out front here with J. And then our main diagonal is A1, B3. The off diagonal is A3, B1. And then the last component is K times this determinant. The main diagonal is A1, B2. The off is A2, B1. And so comparing that with exactly what we have up here, let's just get rid of these highlights. You can see these match up, just some renaming. Same thing here, B1, B3, C1, C3 matches, and these match. Instead of coefficients out front, A1, A2, A3, we have vectors. So these are the things that are going to go into the top row. So really, when I'm taking the cross product, what I'm doing is I'm taking the determinant of the matrix, whose first row is I, J, K, and then the second row are the components of the vector A, A1, A2, A3, and then the third row are the components of B, B1, B2, B3. So instead, I'm going to use this matrix and find the determinant of it to find my cross product, which is way easier because we tend to like having an algorithmic approach as opposed to having some kind of formula that we just need to remember. And determinants are something that doesn't go away. We're going to continue to use them throughout the semester too when we start talking about vector calculus. So let's go ahead and let's find some cross products to get used to this. So starting with our first example, we're going to find both A cross B and B cross A. If the vector A is 1, 2, 3, and the vector B is 2, 4, negative 1, right? Because you're going to see here, unlike the dot product, the order is going to matter for this. So let's start with A cross B. So immediately I go ahead and I put I, J, K on my top row. A comes first, so I'm going to put that in the second spot. So that's 1, 2, 3. B comes second, so that goes into the second spot. And I want to go ahead and I want to take the determinant of this matrix. Now, definitely from here, you're going to take a lot of paper. Don't try to squish everything out. You want to make sure it's clean and legible and easy to follow. So from here, what I like to do is I know I'm expanding along that first row. So I like to kind of prep everything out. We're going to have a matrix times I. Next one's negative. So we're going to prep that matrix, and that will be times J. And then we have the third one, which is positive, times K. So starting with I, I'm going to go ahead and I'm going to cross out everything in the same row and column. And the things that are left are 2, 3, 4, negative 1. Now we do the same thing. For J, we ignore everything in the same row and column. The numbers that are left are 1, 2, 3, negative 1. And then last but not least, ignore everything in the first row and the third column. And my elements left are 1, 2, 2, and 4. So now we need to go through and we need to find these 2 by 2 determinants. So we can go ahead and get rid of that. We want to do the product of the main diagonal minus the product of the off diagonal. So it's going to give us 2 times negative 1 minus 3 times 4. And that's going to be attached to I. At this point, if you would prefer to honestly just get rid of this and jump right into the vector, absolutely you can, because you know the I, J, and K is just representing the first, second, and third component. Completely up to you what you want to do. But I'll go ahead and do it this way, and then I'll jump to using the vector form in the next one. The number one thing that happens is we forget about this minus sign that's in front of the second one. And same thing, we want to multiply the main diagonal, subtract the off diagonal. So that will give us 1 times negative 1 minus 3 times 2. And then this is the J component. And then last but not least, main diagonal is 1 and 4, off diagonal is 2 and 2. So we do 1 times 4 minus 2 times 2. And that is our K component. So here I will now jump into our normal vector form. This is negative 2 minus 12. So that's going to give us negative 14 for I. Got to remember that minus for the second one that's out front. So this gives us negative 1 minus 6. That's negative 7. But that minus will turn it to positive. So the way I like to do is I leave that minus, and then we've got the negative 7. And then thankfully this last one is the easiest, because that is going to be 4 minus 4. So that just leaves us with 0 in the k component. So the cross product is going to be negative 14 times positive 7, or not times, negative 14, 7, 0. Okay, so that is our resulting vector. And you can see if you go ahead and do the dot product with either A or B, you can see that it is going to result in 0, meaning they are orthogonal to each other. So I can quick kind of show you just with this as a note. If I do A dot product with A cross B, the vector A is 1, 2, 3. The vector B, or sorry, A cross B is negative 14, 7, 0. So doing those like components, 1 times 14 with a negative is negative 14. Then we have 2 times 7 is positive 14. 3 times 0 is 0. You see, you end up with 0. So A is orthogonal to the cross product. And then if I change this to the vector B, that is 2, 4, negative 1. So 2 times negative 14 is negative 28. 4 times 7 is positive 28. And then the last component is 0. So you still end up with 0. So you can see this vector is orthogonal to A and to B. So we don't really need that. Now at this point, you can just trust that the cross product is always going to result in a vector that's orthogonal. So let's get some more practice. Let's go ahead and do B cross A. And all that means is we're going to switch which row B and A are in. So B is going to go first. That's 2, 4, negative 1. And then A is 1, 2, 3. So I'm going to show you another way you can do a determinant of a 3 by 3 matrix. Completely up to you what approach you have to do. Just make sure your notation is correct, because in the end, this should result in a vector. So off to the side, I'm going to do just a little bit of scratch work. So we're going to start by just copying the matrix down, ijk, 2, 4, negative 1, 1, 2, 3. And then what you're going to do is you're going to repeat the first 2 columns. So we've got I, 2, 1, J, 4, 2. What I'm going to do is I'm going to mark off some diagonals here. So kind of following the dots, we've got 3 main diagonals. And then looking at the off diagonals, we have 3 of those as well. Okay. What I'm going to do is I'm going to multiply this stuff on the main diagonals. Those are all going to be positive. And then these off backward diagonals are all going to be negative. So what happens here is we'll have on this first one, I times 4 times 3. That results in 12I. Then this one is J times negative 1 times positive 1. So that gives us negative J. And then this last one is 2 times 2 times K. That gives us positive 4K. So these are all of the main diagonals. Now working with the off diagonals, I'm going to subtract all of those. So working with this first one, that's 1 times 4 times K. So it is 4K. This next one, 2 times negative 1 times I is negative 2I. And then this last one is going to be 3 times 2 times j. So that is going to be positive 6j. Okay? So these are all the off diagonals. So grouping those like pieces, I now can go back over here. We've got 12i and then minus negative 2i. That's going to leave us with 14i. Negative j minus 6j gives us negative 7j. And then we've got 4k minus 4k. That's going to leave us with 0k. So the resulting cross product is going to be 14, negative 7, 0. And again, you can do determinants, whatever you want, but this off to the side is scratch work. I don't want to put equal signs here and say that this is equal to this. This is just kind of a shortcut that you're doing off to the side. So the result is that this determinant is equal to this particular vector. And so something you can hopefully see happens is these two vectors end up just being opposite signs of each other. And that makes a lot of sense. There are technically two vectors that are orthogonal to A and B. One is pointing in one direction. The other is going to be just the scalar multiple in the opposite. So the order that you do the cross product in is going to matter because it's going to give you one of those two particular vectors. However, it's always going to result in the opposite sign. So once you have A cross B here, really immediately I can then say B cross A is the same, but I negate all of the signs. So that's one of our special properties for this. And we'll go through properties in general in a little bit. But the next thing we're going to do is we're now going to look at what happens when we take the cross product of the vector with itself. And we're going to actually make this an exercise. We're going to show if we have any vector u and we take the cross product with itself, it's going to result in the 0 vector. So this is for any arbitrary vector u. So the thing you want to be careful with is I don't want to pick numbers for u. This needs to happen for any vector. So what I'm going to do is I'm going to have it be, or have it have arbitrary elements. So to show this is true, I'm going to let the vector u be comprised of a, b, and c, where these a, b, and c are real numbers. So to say they're real numbers, we just say they're an element of R. Then I'm going to go ahead and figure out what is u cross u. So the first row is I, j, k. And then because they are the same, we've got ABC, ABC as our two vectors. So in this one, I'm going to go through the determinant process, not this trick that we just did back here, because I personally like the determinant process more. It's a more standard approach to this. So expanding along the first row gives us I, then we're going to have minus j, and then plus k. And especially when we start to get more complicated determinants, when they're involving functions, this approach tends to work a little bit better. So for my first one, I strike the first row and first column, and that leaves me with BC, BC. Then I strike first row, second column, that leaves me with AC, AC. And then finally, ignoring the first and third, leaves me with AB, AB. And so I'll show you here how we can just immediately jump into the vectors. So I'm going to give myself lots of space. And remember that this middle term is going to have to be negative. So we multiply the forward subtract the backward. So this first one is going to be b times c minus b times c. Second one, forward minus the backwards. So that is a times c minus a times c. And then finally, forward diagonal, backwards diagonal. So we have AB minus AB. So no matter what this vector is, A, B, and C were arbitrary real numbers. The first component is always 0. The second is always 0. The third is always 0. So the result is the 0 vector. So this is nice. Any vector times itself in the cross product is always going to result in 0. Okay. So before we get into the properties, what I want to do is kind of show why this is also important. So we saw in the dot product that when I go ahead and deal with the dot product of two vectors, it plays a role with the angle between those. The same idea is going to happen here. It's just going to involve a different trig function. Now, because we went through already proving what the cross product is and where it comes from, I'm not going to spend the time going through and showing this particular formula because we also did it with the dot product. So you can look this up in your textbook or you can find it online. Just send me an email if you need help with it or want to see. But if I want to find the angle between two vectors, instead of using the dot product, I can also use the cross product. So if theta is the angle between the vectors A and B, then we really have an analogous formula. If I go ahead and take the cross product and that length, kind of like I had A dot B, it's going to be the magnitude of A, the magnitude of B, and instead of cosine of theta, this is going to be sine of theta. So this is where that angle, again, is going to be the smallest possible angle, so it's between 0 and pi. Okay. Now, if the two vectors are parallel to each other, then what's going to happen is because that angle is 0 or pi, sine of theta is going to equal 0, you're going to have that the magnitude of the cross product is going to equal 0. The only way that can happen that a vector will be of length 0 is if it is the 0 vector. So kind of like we have the way to test if two things are orthogonal, we take the dot product. We can test if two vectors are parallel by taking the cross product, and it should result in the 0 vector. So kind of summarize that as a little note. If A and B are parallel, then the angle between them is theta. It's going to be 0 or pi. So what that means is when I plug that into this formula, it's going to give us the magnitude of the cross product is the length of A, the length of B, times sine of 0 pi, which is 0. And so the result will be 0. So the only way this can happen is if the cross product of these two vectors is the 0 vector. Because you're saying the length of this vector is 0. Has to be the 0 vector again. Okay. So the other nice useful thing that happens for this is we can actually talk about parallelograms. So we can see an application of what the length of this cross product is. So now if we draw A and B, so that they have the same initial point. We can create a parallelogram. Because we saw that when we were dealing with the parallelogram law, when we're adding two vectors. But instead, we're going to see a different application here. So we've got our vectors A and B, and we're going to make them have the same initial point. Let's say this one is A, this one is B. And then that angle here is the angle between them. It is theta. So we're going to go ahead and make a parallelogram, meaning this one is going to run parallel to A, and it's going to be the same length. And then this one is going to run parallel to B. So this side length here is the length of A, and this side length is the length of B. When I'm dealing with the area of a parallelogram, the area of pretty much everything is the base times the height. The base in this case is exactly A, but it is the length of that vector. And the problem is I have to find the height here. So I need the distance between these 2 points, and that should be like a nice right angle. So we'll call this H. So it is the length of the vector A times the H. What I need to do though is write this in terms of the things I know, which is A, B, and the angle between them. So just kind of working with this right triangle we have here. If I take sine of the angle theta, it's equal to the opposite, which is H, over the hypotenuse, which is the length of the vector B. So really, this value of H, we can rearrange. It is B times sine of theta. Okay? So since the height is H, which is the magnitude of B times sine of theta, we get the area of the parallelogram is the following. The area is going to be magnitude of A times the height, and we know the height is really the magnitude of B times sine of theta. But that is exactly what is on the right-hand side of this equation. So instead, I can condense this. I do not need to figure out what sine of theta is, or I do not need to figure out the angle between them. Instead, this is the magnitude of the vector A cross B. So if I want the area of the parallelogram, all I need to do is find the cross product of these two vectors, and then I'm going to find the magnitude. It makes zero difference which one you put to be first or second. You could find B cross A, because once you take the magnitude, that minus sign isn't going to matter, because remember, they're just opposite signs. So let's see an example of this. It's not quite a parallelogram, but we can still utilize the same process here. Let's find the area of the triangle with vertices P, which is 1, 2, 3, Q, which is 2, 3, 1, and R, which is 3, 1, 2. Now, I definitely don't want to plot these in 3D, so instead I'm going to go ahead and I'm just going to draw a little bit of a picture. We've got 3 points, which I'll call P, Q, and R. So we want the area of the triangle that's formed by these three pieces. So that is this area in here. So what I can do instead, let's make this a little bit thicker, is if I find this vector here, PQ, and this vector here, PR. If I take the cross product of those and find that magnitude, that's going to result in the area of the parallelogram. So it is this parallelogram formed here. If I'm looking for the triangle, all that is half the area of the parallelogram. So the area of the triangle is half the area of the parallelogram. Formed by the vectors PQ and PR. And again, you can really make this any vectors you want. You could find RP and you could find RQ. Go ahead and take their cross product and then find the length of that. Completely up to you what you want to do. But it makes sense for me to just kind of do things alphabetically, PQ and PR. So remember, if I want to find these vectors, all I'm going to do is take the terminal and subtract the initial. So for PQ, I'm working with these two. I want to do Q minus P. So the first component is 2 minus 1. Second component is 3 minus 2. And the third is 1 minus 3. So this vector is 1, 1, negative 2. Now to find PR, I'm working with these two, and I want to do the R coordinate minus the P coordinate. So that will be 3 minus 1, 1 minus 2, and 2 minus 3. So that gives us the vector 2, negative 1, negative 1. Now I'm going to go ahead and I'm going to take the cross product of these two. And again, doesn't matter which one you pick to be first. So putting our I, J, K, PQ is 1, 1, negative 2, and then 2, negative 1, negative 1. And again, I always like to do the determinant version of this because it helps me not forget minus signs too. So we've got our first matrix, I, minus the second matrix, J, plus the third matrix, K. And then we go ahead, cross out everything dealing in the same row and column as I. That leaves us with 1, negative 2, negative 1, negative 1. Then we go ahead and cross out first and the second column, and that leaves us with 1, negative 2, 2, negative 1. And really every single time the first row is staying out of it. So now we cross out the third column, and that leaves me with 1, 1, 2, negative 1. So now at this point, I'm going to go ahead and just jump into my final resulting vector. So we multiply and subtract. So 1 times negative 1 is negative 1, and then we minus negative 1 times negative 2, which is positive 2. But we're subtracting it. Then we have a minus in the middle, multiply, multiply. So 1 times -1 is -1. Then minus 2 times -2 gives me a -4, so that becomes plus. And then in the last one, multiply, subtract, multiply. So 1 times -1 is -1. 2 times 1 is 2. So that gives us -3 in the first spot. Then we've got +3, but a minus. So -3, and then -3 in the third. So now that I have my cross product vector, I'm going to go ahead and find its magnitude, and the area of the triangle is going to be half of that. So the area of the triangle is A. It is 1/2 the length of the vector PQ cross PR. And so we got 1/2. We're going to have a giant square root. That gives us -3 squared plus -3 squared plus -3 squared. So really it is 9 plus 9 plus 9. So it gives us 1/2 the square root of 27. Which, yes, you can simplify. You can write it as 9 times 3 and simplify the square root. But I personally don't care if you do that. And then your homework isn't going to typically care. If it does, let me know. So now that we got lots and lots and lots of practice with this cross product, let's go ahead and go through all of the properties with it. Again, up to you whether you're going to use these, but there is one property we're going to dive into a little bit deeper because it does have an application to it. So let's look at our properties of this cross product. So we're going to let A, B, and C be vectors. And D is a scalar. Then the following are going to hold. First one is if you take A cross B, it's going to be the opposite sign of B cross A. If I want to do a scalar multiple times A and then cross product it with B, you can worry about the scalar multiple after you do the cross product. Or again, you can put the scalar multiple attached to the second vector instead, so it moves around. If you want to do the vector A cross product with the sum of two vectors, you can indeed distribute, but the order is going to matter. So A is going to stay in the front position. You do A cross B, and then add A cross C. If you want to do the opposite and do the addition and then the cross product, same thing is going to happen here, but C is going to come in that second position. So it distributes, but because the order matters, we have to be careful. So you would do A cross C plus B cross C. This next one is the one we're actually going to see an application of. If you want to do the dot product after you do the cross product, okay? Think about what this is going to result in. B cross C is a vector, and then I'm going to dot product it. The end result is going to be a scalar, and this thing is going to make sense. It's a multiplication I can actually do. What we could actually do instead is kind of rearrange this a little bit. Instead, we can do A cross B, and then we can dot product it with C afterwards. So it's kind of like a rearrangement. And then our final property is if I do A cross B cross C, we can actually do something real funky with this. So if you notice, B cross C will be a vector. Then once I do the cross product here, the result is a vector. So we can actually rewrite this as A dot C, which is a scalar, times the vector B, minus A dot B times the vector C. So these two are going to be scalar multiples of B and C, and then when we do that combination of the two, the result is still a vector. So kind of an interesting property that ends up holding. Are we going to use many of these? Not too many, except for this one. This is nice and useful for us. But we're going to take a deeper dive into what is this thing, okay? So in 5, this formula that we get, we call this expression A dot B cross C, which results in a number. This is the scalar triple product. Or you might also hear it called the triple scalar product. It really doesn't matter which one you do. Okay? So to just give you an idea of what ends up happening here, the result is a number. A dot C, or A dot B cross C, means you're going to take A and you're going to dot product it with the result of this determinant, which is I, J, K, and then B1, B2, B3, C1, C2, C3. So really what ends up happening is when you do this dot product, A1 is going to be dot product with the result of the I component of that cross product. So what ends up happening, if I go way back up here, is you get this matrix and then you're going to times it by A1. You get this matrix and it's times A2. This matrix times A3. So really what ends up happening is this first row, because it results in a scalar, is going to end up being replaced by A1, A2, A3. So ultimately, you're finding the determinant of this 3 by 3 matrix. So this determinant actually has some geometric significance too. So we're going to go ahead and look at what that is. So the triple scalar product has geometric significance as a volume. So if I have 3 vectors, A, B, and C, and let's assume they all have that same initial point. Let's say A goes up in this direction, say B goes here, and let's say C goes backwards. So this is A, this is B, this is C. What we can actually create is something called a parallelepiped. So you know 2 vectors can form a parallelogram. You add that third dimension, it's basically a 3D parallelogram. So the 3 vectors form a parallelepiped, which is a fun word to say. When you're thinking about the volume of something, it's the area of the base times the height. So the volume is V, which is the area of the base times the height. And if you think about the base of this thing, it is a bunch of parallelograms. Really, every side of this thing is a parallelogram. So to give you a ghost sketch of what this looks like in 3D, this would run parallel to both of these sides. And then we have the back side here, which runs parallel. And then this side here. Not the best drawing, but that's okay. Then we have this side, which runs parallel to C. And then we have the other pieces of this. So it is a bunch of parallelograms. They should all be parallel to each other. So let's rewrite this over a little bit. So the area of the base in this case is the area of the parallelogram formed by B and C. So the area of the base is the area of the parallelogram. Which we know the area of the parallelogram is the magnitude of the cross product. So in this case, because B and C we're taking to be our base, it is the magnitude of B cross C. Now the height, however, is a little bit harder. That's the distance from the bottom to the top. So instead what I'm going to do is I'm actually going to consider the height to be out here, H. And imagine we've got a straight line over here. Then this angle here, I'm going to call theta. Okay? So the height is H. Which I can write in terms of A and the angle between H and the vector A. So cosine of theta would be the opposite or the adjacent over the hypotenuse. In this case, the hypotenuse is A. So rearranging it, H is the magnitude of A times cosine of theta. So ultimately what happens is our volume is going to be area of the base times the height. Okay, and then I'm just going to rearrange this. I'm going to put the A out front. And then if you notice this formula, you've got a magnitude, cosine of theta. And the other thing I'm going to do, just to make this, because we want this height to be positive, we're going to assume that this makes it positive. This really looks like our angle between two vectors formula. The problem is this theta would be the angle between A and B cross C. But what I have right here is theta is the angle between H and A. However, because this is the third dimension, remember the cross product gives you a vector that's orthogonal. So this vector, B cross C, will be in the same direction as H. So B cross C will point in this direction. So in reality, these two vectors are, or that angle theta is the angle between A and the vector B cross C. So what I can do instead, remember this turns into this, wrong tool, this vector dot product with the other one. So we can simplify this and say the volume of this parallelepiped is really A dot product with B cross C. Okay? So if I find the triple scalar product, that's going to tell me the volume of the parallelepiped. It is possible that this would be negative, but since it's a volume, all you do is just take the positive case of it. So I think you'd be comfortable just kind of like we did with the last example. You can find the area of a parallelogram. We use it to instead find the area of a triangle. you can use this triple scalar product to find the volume of a parallelepiped. Instead, I'm going to do a different application of it. So we're going to go through and we're going to look at the example that wants us to figure out or determine if the vectors are coplanar. And the vectors we're given are A, which is 1, 2, 3, B, which is 2, 1, 3, and C, which is 3, 1, 2. Now, coplanar means they all lie in the same plane. So if that's the case, here is our plane, and all 3 points, or all 3 vectors, are in here. Okay. Now, the way I can relate this to the triple scalar product or the volume of a parallelepiped, if things are coplanar, that means they're in 2 dimensions. So if that's the case, if I go to find this volume of the parallelepiped, it should be 0 because it's not 3-dimensional. So if the vectors are coplanar, meaning it's a 2D object, then the volume of the parallelepiped they form is 0. So what we're going to do is we're going to find the volume of the parallelepiped, which is just the triple scalar product. Okay. If I find this is 0, they're coplanar. If it actually has a volume, that means these things don't lie in the same 2-dimensional space, so they are not coplanar. So we want to do A dot B cross C. You absolutely can go about this by finding B cross C and then dot producting it with A, but instead you can also jump into just that 3x3 matrix, and it just goes in order. So we put vector A in the first spot, which is 1, 2, 3, then vector B, which is 2, 1, 3, and finally vector C, 3, 1, 2. And honestly, it makes no difference what order you switch these in, because in reality, if it turns out to be negative, the volume is just the positive case of that. And if you remember from pre-calculus, going over determinant formulas, if you just switch rows within a matrix, all it does is potentially change the sign of the determinant. So it won't do anything to the actual number itself. So you really could put B, then A, then C, whatever you want. But I like keeping it simple and just doing exactly what we have. Okay. So we're going to go ahead and do that expansion along the first row. So I'm going to have a matrix times 1. Then we subtract another matrix times that second value, which is 2. And then we add a third matrix times that final value of 3. To figure out what goes in, we ignore all of these, and what's left over the first one is 1, 3, 1, 2. For the second one, we ignore the second column, and what's left is 2, 3, 3, 2. Then for the third one, ignore the third column. We're left with 2, 1, 3, 1. Now I can just jump into going through this. The result in this case, remember, is not a vector because we don't have I, j, or k left over. So I can't just jump and write a vector now. So instead, we're going to do product minus the product. So that gives us 2 minus 3 times 1. Then we've got minus, we'll do the next one in purple, product minus product. So that will be 4 minus 9, and then times 2. And then the last one is plus product minus product. That will be 2 minus 3 times 3. So 2 minus 3 is negative 1 times 1. 4 minus 9 is negative 5 times 2 is negative 10, but that minus out front turns this to plus 10. 2 minus 3 is negative 1, and then times 3 is minus 3. So really this gives you 10 minus 4, which results in 6. So what that means is the volume of the parallelepiped formed by these is positive, so it does have to form a 3D shape. So because of this, the vectors are not coplanar. So hopefully you feel pretty good with these operations so far. What we're going to do in the near future is we're going to talk about how do I deal with lines and planes in space on a more like formula level, like what does the equation of those things look like? And then we're also going to jump into a lot of three-dimensional figures.